Hello, I'm Dr. Karen Matika. This presentation on the nucleic acid extraction technique, salting out, has been prepared for the University of Alberta. The University of Alberta is located on Treaty 6 territory. Treaty Number 6 was signed on August 23, 1876 at Fort Carlton in Saskatchewan. The total area of the treaty stretches from western Alberta through Saskatchewan and into Manitoba, and includes 50 First Nations. The presentation uses material that is not my own. Copyrighted material contained herein is reproduced under subsection 29 through 29.4 of the Canadian Copyright Act. This presentation is available for your individual use. Further distribution may infringe copyright. The content of this presentation applies to Competency Category 3, Pre-Analytical Phase, of the 2024 CSMLS Pan-Canadian Competency Profile. In particular, Competency 3.4.5 states that a clinical genetics medical laboratory technologist prepares specimens for analysis, including the extraction and isolation of nucleic acids. If you are preparing for the American Society of Clinical Pathology's board exams for molecular biology, the content of this presentation would apply to Section 2, Molecular Techniques, Category A2, Manual Nucleic Acid Isolation Techniques. For this presentation, we have 4 overall learning objectives. By the end of the presentation, you should be able to discuss the principle of salting out, list commonly used salts and their uses, list the advantages and disadvantages of ethanol and isopropanol, and discuss carrier molecules. DNA's structure and biological functions are dependent on its hydration. Solvating water molecules surround DNA through dipole-dipole interactions. Water is also found in the minor and major grooves of DNA. Water molecules within the minor groove of DNA are structural and form a chiral spine of hydration. In the image in this slide, the minor groove water is represented by the red, while the blue represents water in the major groove. Under physiological conditions, each DNA nucleotide carries a charge of 1 electron. This is a property of the phosphate groups of the nucleotides. Cations preferentially bind to guanine bases in the major groove or to oxygen atoms in the phosphate groups. The image on the slide illustrates regions of high sodium ion density around an aqueous DNA molecule. The yellow dots surrounding the DNA represent sodium ions. Cations stabilize condensed DNA, providing electrostatic screening for the highly charged naked DNA, and even facilitates the attraction of light-charged DNA molecules under certain conditions. Several different salts can be used in the salting out procedure. The salting out procedure may often be referred to as the alcohol precipitation of nucleic acids. The most common salt is sodium acetate at pH 5.2. A 3 mole per liter stock solution is added to a nucleic acid solution to achieve a final concentration of 0.3 moles per liter. Lithium chloride is highly soluble in ethanol. It is commonly used to precipitate large RNA molecules. When the DNA or RNA solution contains sodium dodecyl sulfate, sodium chloride should be used for the precipitation. If the solution also contains free nucleic acids or oligosaccharides, ammonium acetate is preferred for precipitation. However, ammonium ions can interfere with some enzymes in downstream procedures. Following the addition of a salt to a nucleic acid solution, an alcohol is added. Ethanol and isopropanol are routinely used to precipitate nucleic acids. Both alcohols have low dielectric constants. For example, ethanol's dielectric constant is 1/3 that of water. The lower dielectric constants of the alcohols allow cations to get closer to the DNA. The cations negate the negative charge of the DNA. This allows the nucleic acid molecules to come closer together and to precipitate out a solution. Precipitation can be facilitated by centrifugation. Both ethanol and isopropanol are commonly used to precipitate or salt out nucleic acids. In general, ethanol is preferred to isopropanol. This is because ethanol is less viscous and subsequently it will evaporate off the precipitated nucleic acids more readily than isopropanol. Also, salts are more soluble in ethanol, so when the ethanol is removed from the precipitated DNA, it's more likely to take the salts with it, thus your nucleic acids are more likely to be salt-free. Isopropanol is preferred when you're precipitating DNA from a larger volume. This is because you need more than 2 volumes of ethanol per volume of nucleic acid solution, whereas with isopropanol, you need approximately 1 volume of isopropanol to the nucleic acid solution volume. The figure on this slide depicts 2 DNA molecules under 3 different conditions. In the water droplet on the left, the 2 DNA molecules are repelled by one another. This is a result of the negative charge on the molecules imparted by the phosphate backbone. In the middle image, a sodium salt has been added to the nucleic acid solution. Note the sodium ions are attracted to the DNA but are kept at some distance from the DNA due to the dielectric constant of water. In the image on the right, the DNA is now in an ethanolic solution. The cations, the sodium ions, can get closer to the phosphate backbone. This negates the overall negative charge of the DNA molecules, and the molecules can get closer together. Carrier molecules are added to nucleic acid precipitations to enhance yield. These substances are insoluble in alcohol and trap nucleic acids when they are centrifuged. Common carriers are yeast transfer RNA, glycogen, and linear polyacrylamide. The table on this slide outlines their use. This slide image shows the precipitation of DNA with ethanol, or the salting out of DNA. In tube 1, we have a solution of DNA, so our cells have already been lysed and our DNA is free in solution. Next, we're going to add sodium acetate to a final concentration of 0.3 moles per liter. So we start with a stock solution of 3 moles per liter, sodium acetate at pH 5.2, and we're going to add the sodium acetate to a final concentration of 0.3 moles per liter. We're going to mix that, and then we're going to add 2 volumes of 95% ethanol. Again, we're going to mix, followed by centrifugation at maximum speed for 10 minutes. Next, we remove the supernatant and discard it, and we are left with DNA on the side of our tube. We're going to half fill the tube with 70% ethanol. This is an ethanol wash step. The 70% ethanol will get rid of any residual salts that have been precipitated with the DNA. We're going to centrifuge that, and then we're going to remove the 70% ethanol. We're going to repeat this step once. So again, we're going to half fill the tube with 70% ethanol. We're going to centrifuge it and aspirate off the supernatant. Now we're going to resuspend our DNA off the side of the tube in an appropriate buffer or in molecular grade water. In summary, DNA and RNA can be salted out of an aqueous solution by using a combination of salts and alcohol. The alcohol, usually ethanol or isopropanol, reduces the dielectric constant around the nucleic acids. This allows the cationic salt to move into closer proximity so that the salt neutralizes the net negative charge of the nucleic acids. By removing the net negative charge of the nucleic acids, the nucleic acid molecules can move closer together and precipitate. Precipitation is facilitated by centrifugation. The following references were used in the preparation of this presentation.